Hi everyone, welcome to my YouTube channel. I am Madam Rosmaya. I am a Form 6 teacher at SMJK Yuhua Kajang. So in this video, we are going to discuss on magnetic fields. So the subtopic is determination of the ratio E per M for electrons in Thomson experiment. So the objective for this video is students should be able to describe the principles of the determination of the ratio E per M for electrons in Thomson experiment, and also we are going to solve problems given. Okay, refer to the diagram here. This is a cathode ray tube. So in the cathode ray tube, we have here the cathode where it supplies or emits electron from the filament here. Then the electron is accelerated towards anode, and then it pass through the magnetic field and also the electric field. So what happened? We can adjust the flow of the electron through this electric field and magnetic field, so that it managed to reach the fluorescent spot here, the display here. Okay, we have a deflection scale here, so that we can make sure where the points, the spot we can see. Okay, so who discovered the electron? So here is the picture of Joseph John Thomson. So the discoverer of the electron. Okay, so this is the path with the magnetic field. So the electron flow through here and this area if in the presence of magnetic field only by the magnet here. So if you use Fleming's left hand rule, okay, the electron flow this way. So the middle finger shows direction of the current to the opposite side, because electron this way, so means to the right. So current is to the left. And then next, the magnetic field north to south, okay, shows by the point finger or forefinger. Then lastly, refer to the magnetic field direction. Okay, magnetic force direction, not magnetic field. Magnetic force is upward. Okay, therefore the electron in the presence only magnetic field, it will deflect upward. So when we see through the fluorescent spot here, it will be here on top. Then if we switch off the magnetic field, okay, the electron will flow only in the presence of electric field. So what happened to the electron? So the electron will flow in this path, the second path. So why? So because the electron attract to the positive plate. Okay, this is the plate. So we have negative plate and positive plate. So the electron will attract to the positive plate. So that's why the electron follow the path, and this is the projectile path actually. So what happened in the display here on the cathode ray tube? So the spot we can see at the bottom of the screen here. Okay, if we switch on both magnetic field and electric field, and we adjust the strength of the magnetic field and the electric field, we can adjust until the electron manage to flow in the straight path. Okay, this is path where with fields and the magnetic field and magnetic field and electric field counterbalance. When both fields counterbalance, the magnetic force is equals to the electric force. Okay, magnetic force formula is given by EVB. E is the charge of electron, B is the speed of electron, and B is the magnetic field strength. And formula for electric force is QE. In this case, we use electron, so electron times E. E is the electric field. So we can cancel out E. So we have V equals to E per B. So this is the speed of electron. So refer to the diagram here. We have plate negative on top, positive plate at the bottom. So the electron move with velocity v in a straight path in the presence of both electric field and magnetic field where they are balanced. So when V is turned off, this is the flow of the path, and electric field direction, electric force direction is downward because electron attract to the positive plate. So let's say the length of the plate here is L, and we assume that in the middle here, the length of the electron from the middle to this part is half of the L, and the distance here, or the arc here, okay, when the electron spot is at the bottom in the presence of the electric field only, so the distance from the center down here is y, and the distance from the center of the plate here to the display here on the cathode ray tube display, so let's say x. So the distance here at the end of the plate here is let's say s. So we are going to find s. So we can use formula s equals to ut plus half at squared, because the path followed by the electron here is the projectile path. So we can use this formula s equals to ut plus half at squared. So A can be found by using F equals to MA. So F is EE equals to MA. So A is electron charge times electric field per M. Okay, we substitute into here. And then T is the length times speed. Okay, so time taken for the electron to from this point to this point. So length of the plate here divided by the speed. Okay, we get time taken. So now we substitute into the equation. Here we get S equals to half 0 plus half E electric field L squared per mv squared. U is 0 because initial value of speed. Then S equals to E electron charge electric field L squared per 2 mv squared. Okay, now we get S. Okay, next we are going to relate with V equals to E per B. Okay, from the triangle here, this assumed as a triangle, so we can use similar triangle concept. Okay, so S per Y, ratio of S per Y is equals to ratio of L per 2. Okay, L per 2 per X. Okay, L per 2 and per X. So we use similar triangle concept. Okay, next we cross multiply, so you get S equals to Ly per 2X. Okay, now we can substitute this S into here. So we get this. Then we also substitute V equals to E per B into the equation here. So we get this, and we simplify this equation so that we can get E per M. So E per M equals to the rest of the variables we bring to the right side. So the equation become E per M equals to EY per XL B squared. Okay, so what is this E per M? This is a specific charge, electron per mass. E, Y, X, L, and B are measurable. So we can get the value of specific charge, electron per mass, or the ratio of electron to mass. Okay, so we try one example. Let's read together first the question 1. In Thomson's experiment, a beam of electrons traveling at 6.8 times 10 to the power of 7 meter per second is bent into a circular path of radius 4 centimeter in a magnetic field of induction 10 to the power of negative 2 Weber per meter squared, normal to its path. So find the specific charge, which is E per M, ratio E to M. Okay, so you are given the speed of the electron and radius of the path taken, circular path taken if in the presence of magnetic field only, which is 10 to the power of magnetic field of induction, 10 to the power of negative 2 Weber per meter squared. And this is B. Okay, so besides Tesla, the unit for similar to Tesla, we can see as Weber per meter squared. It's the same thing. So magnetic field unit can be Tesla or can be also written as Weber per meter squared. Okay. Okay. Now, so now we are going to find ratio E to M, or in other words, specific charge. Okay, because of radius is given, this is a keyword, okay, radius. So we can use centripetal force. So centripetal force is mv squared per r, and it is provided by the BeV. Okay, so magnetic force. This is magnetic force. In the presence of magnetic force only, so the centripetal force is provided by the BeV. Okay, so now we bring M to the right side and become E per M. So equals to V per BR. We arrange the equation here because we are going to get the specific charge. So therefore the specific charge is, we substitute this V and then the B and also radius. Don't forget to convert the radius to meter. So we get specific charge equals to 1.7 times 10 to the power of 11 coulomb per kilogram. So the unit for electron electric charge is charge of electron is coulomb, mass is kilogram. Okay, done for question 1. Okay, now we try question 2. Okay, in Thomson's experiment, a beam of electron traveling at 2.652 times 10 to the power of 7 meter per second is bent into a circular path in a magnetic field of induction 0.5 Weber per meter squared, or the unit is Tesla for magnetic field, and it's normal to its path. Find the radius of circular path if E per M is equals to 1.76 times 10 to the power of 11 coulomb per kilogram. Okay, so you are given the speed and then the magnetic field and then the specific charge, ratio E to M. Okay, from here we can find, we are going to find radius. Okay, we are going to find radius. Because we are going to find radius, so again we can use centripetal force. Okay, BeV equals to mv squared per r. Okay, so r is Vm per Be. We arrange the equation here so we can find r. Okay, so we substitute all the values given. Because specific charge is given, so we bring M down, so become E per M. Okay, so this is specific charge. Okay, now we can substitute V, 2.652 times 10 to the power of 7, magnetic field 0.5, and the specific charge is 1.76 times 10 to the power of 11. So the answer is 3.01 times 10 to the power of negative 4 meter. So this is the answer for the radius of the circular path. Okay, now let's try the third example. The question given, an electron beam is produced by an electron gun in which each electron is accelerated through a potential difference of 1.6 kilovolt. When the electrons pass at right angle through a magnetic field of flux density 8.0 millitesla, the radius of the curvature of the electron beam is 0.017 meter. So determine the specific charge of the electron, E per M. Okay, you are given electron, potential difference 1.6 kilovolt, magnetic field 8.0 millitesla, radius of the curvature 0.017, and we are going to determine specific charge. So what formula are we going to use here? Because potential difference is given, electron is given, so we use principal conservation of energy. So where the kinetic energy is equals to the supplied energy, EV. Okay, so this potential difference across the cathode and anode, where the electron is accelerated, and then the kinetic energy of the change in kinetic energy, and it is the work done equals to EV. So we also going to use the radius because the keyword here radius, so that's mean centripetal force involved here. So we can use BEV equals to mv squared per r, where the magnetic force provide the centripetal force. Okay, so we arrange the equation here. V squared equals to 2EV per m, and here BE equals to mv per r. Okay, now we squaring both sides because we are going to substitute V squared into here. So we square this both sides. So we get B squared E squared equals to m squared V squared per r squared. Okay, so now we can substitute V squared into here. Okay, so I write here. So we substitute into V squared. So we get this. Now we can simplify this to get E per m. Okay, so we get the ratio E to m, or specific charge, equals to 2 V potential difference per B squared R squared. Okay, so now all these values is given, so we can substitute into the equation here. So V is 1.6 kilovolt, convert to volt, and B is 8 millitesla, so convert to Tesla, and the radius is 0.017. So we get specific charge equals to 1.73 times 10 to the power of 11 coulomb per kilogram. So this is the answer for this question. That's all for the video, and thank you for watching. Bye.